Today our goal is to prove Egorov theorem in measure theory. Okay, it's a Russian name. So this is a very famous theorem in measure theory. But before proving or stating this theorem, what we are gonna do, we are gonna define point-wise convergence in terms of the union and intersection. So point-wise convergence. Okay. So let we have a measure space X, S, and mu be a M space. M space means measure space. Let we have a sequence of function be a sequence of measurable functions on X. Then Fn of X approaches to Fn of f of X. Okay. Point-wise, what does it mean? Means for all epsilon greater than to 0, there exist n belong to natural number such that for all n is greater than natural number n, okay, Fn of X minus f of X is less than epsilon. Also we can put that in this way. Okay, so for all x belong to X, instead of epsilon, for all k belong to set of natural number, there exists n belong to n such that for all n is greater than n, Fn of X minus f of X is less than 1 divided by k. Now what we can rewrite this thing, so for all k belong to set of natural number, there exist n belong to n such that X belong to, since for all n is greater than, so for all we use intersection, so n is equal to n up to infinity, and this would be f of n of X minus f of X is less than 1 divided by k. And now this means that for all k belong to n, okay, so for all k belong to n, now again since we have there exists, so we can use union, that X belong to union of n is equal to 1 up to infinity intersection of n is equal to n up to infinity. We have Fn of X minus f of X is less than 1 divided by k. Right? Moreover, we can rewrite this thing that X belong to again intersection, so k is equal to 1 up to infinity union n is equal to 1 up to infinity intersection n is equal to n up to infinity. We have Fn of X minus f of X is less than 1 divided by k, and this is nothing but this is X, which is intersection k is equal to 1 up to infinity union n is equal to 1 up to infinity intersection n is equal to n. X belong to X such that Fn of X minus f of X is less than 1 divided by k. So this is what we have for point-wise convergence in terms of union intersection. Now we are ready to state and prove the Egorov theorem. That's what we need. Okay, so that's just the point-wise convergence in terms of union and intersection. So now Egorov's theorem says that, so Egorov's theorem, so this is a very important theorem. So since we have already, so we will again rewrite, let X S mu be a measure space. Okay, let measure of X is finite and Fn approaches to f pointwise. Okay, for then for every epsilon greater than to 0, there is a set G belong to sigma algebra such that number first condition a measure of x difference G is less than epsilon. Okay, and the second thing will be f of n approaches to f now uniformly, but where? On set G. That's what Egorov theorem is. So since we got the idea of the pointwise convergence, so we can easily prove this result now. Very famous and important result. So proof is let epsilon greater than to 0 be given, right? Now since, okay, so we know that since fn approaches to f pointwise, so then we know that so for every k belong to set of natural number, x is actually nothing but this is union of n is equal to 1 up to infinity intersection of small n is equal to n up to infinity. What we have x belong to x such that fn of x minus f of x is less than 1 divided by k. Okay, so we're gonna assume that okay, this is nothing, so this is my E capital N K. Okay, this is, so this set is intersection of n is equal to n up to infinity, x belong to x, okay, fn of x minus f of x is less than 1 over k. Now what do we think? So we are going to use previous result as well, so but I will definitely recall those results. So then what do you think about, so if n is equal to 1 we have e1k, if n is equal to 2 we have e2k up to so on. What kind of relation we do have? Clearly I would say that e1k is containing e2k is containing e3k, right, up to so on. Now what kind of sequence we have this one? So this sequence is, what kind of sequence is this? Is an increasing sequence of sets, and make sure that since each fn is measurable, so these e sets are measurable, okay, because the intersection of measurable set is measurable. But so this is an increasing set. Now if you can recall, so if we can recall that if we have e1, if we have sets e1 is containing e2 is containing e3, okay, so then what was it measure of union of, suppose k is equal to 1 up to infinity ek, this was nothing but this was limit k approaches to infinity measure of ek. So in a similar way, now what we have, so we have measure of union of n is equal to 1 up to infinity e and k is actually limit n approaches to infinity measure of e and k, okay. But if you can see, what is this union of n is equal to 1 up to infinity e and k? This was nothing but this was measure of x, right? We defined it. So this is limit n approaches to infinity measure of e and k. But definitely, since our supposition was measure of x is less than infinity, so limit n approaches to infinity, measure of e n k is actually measure of x is less than infinity. Now we have an increasing sequence of sets. We saw that e1k, e2k, and the limit is going to mu of x. So we have an increasing sequence. Then we can clearly see that then, since the limit is going to mu of x and we have an increasing set, then there exists so n which is dependent on k, okay, such that measure of x is less than measure of, so what do you think of the measure of e n, but now n is dependent on k plus epsilon divided by 2k. That's just assumption. You're gonna see why we have plus epsilon divided by 2k, because this limit is going to mu of x, so we say that okay, mu of x is bounded by this number. Now what is this? This is nothing but, if we can rewrite it, this is measure of e n is function dependent on k is less than epsilon divided by 2k. Now how can we rewrite it? This is nothing but this is measure of x difference e n is a function of k dependent on k, this is less than epsilon divided by 2k. Okay, so now what we are gonna do, since the theorem was that we need to come up with g such that measure of x is, so we can define g. So let g is the intersection of k is equal to 1 up to infinity e n is dependent on k. Now our goal is measure of x difference g is less than epsilon. Okay, so now measure of x difference g is measure of x difference g is nothing but this is k is equal to 1 up to infinity e n k. Now by De Morgan law, so I would write it for you guys. Now by De Morgan's law, this is nothing but this is measure of, so by De Morgan law, so this is union of k is equal to 1 up to infinity x difference e n k comma k. Now if we know that measure of a1 union a2 is always less than or equal to sum of k is equal to 1 up to infinity measure of x difference e n k. But now what is this? This is nothing, this is less than epsilon divided by 2k. So k is equal to 1 up to infinity, this is less than, okay, epsilon divided by 2k. But what is this epsilon divided? This sum is nothing but epsilon. So that's how we prove that. Hence, so measure of x difference g is less than epsilon. That's first part of theorem. And second part of theorem is very obvious, to show that now it remains to show that fn approaches to f what, like uniformly on g. So what was g? G was nothing but this was k is equal to 1 up to infinity e n function of k comma k. This was what was this? This was our g. So if I want to show f n approaches to f on g, so definitely I would say let x belong to g. What does this mean? This means that x belong to intersection of k is equal to 1 up to infinity e n is a dependent on k. Okay, now what does this mean? This means that to intersection we can say that for all k belong to set of natural number, x belong to e and k. If something is an intersection, it is for it is in every set. So for all k belong to n, x belong to e and k comma k. Now if since what is e and k, now if you can recall what is e and k was nothing but it was actually the intersection of n is equal to n, so x belong to x. Okay, that was something. So now x belong to e and k comma k. What does it mean? Again it means that, so definitely for all k belong to set of natural number, there exist n k belong to set of natural number n, and for all n belong to definitely n, so x belong to f of n minus f is less than 1 over k. That's what we have, if you look at the definition of e and k. And now definitely, so we can have from here, like, because now n is dependent on k, so that's what actually we require for uniformly convergence. So definitely I would say for x belong to g, for all k belong to n, there exist n k belong to set of natural number, and for all n is greater than n, implies that fn of x minus f of x is less than 1 divided by k. What does it mean? Since n is dependent, this means that fn approaches to f uniformly. So this uniform was very obvious, but I proved it for you guys. So